Hi class, and welcome to chapter 2, which will be about the chemical basis of life. So this will be talking a lot about chemistry. I'm assuming that many of you might not have had chemistry yet, so we'll probably break this chapter into 2 parts, and we'll just go over the first part in this. So they might be a little shorter, but I just want to give you some time to kind of digest the information first before we move on to more. So chemistry is really kind of some would say the language of science, because all science has to do with chemical compounds and atoms and molecules. And one example of how chemistry is important to life in biology is when we talk about rising atmospheric carbon dioxide levels and whether they will harm coral reefs or not. And we'll find out towards the end of this PowerPoint. So the question will answer, how might a chemical compound in the air like carbon dioxide harm coral reefs? And the answer is chemistry. When carbon dioxide dissolves in water, for example, in the oceans, it will react with the water to form an acid. And that chemical reaction will then form acid, which can disrupt the formation of coral skeletons. So coral reefs will not form as easily as they should. So the big ideas in chapter 2 that we'll talk about, we're going to talk about elements, atoms, and compounds. And then we'll talk about how these elements and atoms are bounded together in what we call chemical bonds. So this is H2O, which is water. H2O means 2 hydrogen atoms are bonded with an oxygen atom to create water. And because of this structure of H2O, it kind of looks like a triangle. It's bound together by its electrons, which are these little blue circles. Because it makes this kind of triangular shape, it gives water very specific and important life-supporting properties that we'll talk about. So let's first talk about what an element, an atom, and a compound is. Living organisms are all composed of what we call matter, and matter is composed of chemical elements. About 25 elements are essential for human life, and 4 elements make up about 96% of the weight of most living organisms. When we talk about a compound, then, a compound is a substance consisting of 2 or more different elements in a fixed ratio. So organisms are composed of elements, usually combined into compounds. So for example, if we take the element sodium and we combine it with chlorine, we'll get sodium chloride, which is table salt. Sodium and chlorine by themselves are not table salt, but when you combine them together, they interact in a way where they're bound together by chemical bonds to form little tiny crystals known as sodium chloride or table salt. Here's a look at a diagram listing the percentages of elements that the human body is made up of. You can see oxygen has the highest percentage, and then carbon, hydrogen, and nitrogen. Those are kind of the top 4 that make up the body: oxygen, carbon, hydrogen, and nitrogen. But you can see here there's many other elements that make up the body as well. And when we say make up the body, these elements will combine to form compounds, which will combine to form different molecules, which will go on to form proteins that really make up all the tissues in your body, the organs in your body, all the cells in your body. Some trace elements are required to prevent disease, and trace elements can be common additives to food and water. Fluoride is usually added to municipal city water and dental products to help reduce tooth decay. There's a lot of talk now that fluoride might not be as good for you as they think, but that's another topic. Several chemicals are added to food to help to preserve it, especially in meats. And if you're really concerned about nutrition, you might hear a lot about how preservatives aren't very nutritious and good for the body because they're unnatural. But years ago, these chemicals were really important to add to food to help preserve it in terms of getting food to last longer to feed a family in an age where there wasn't as healthy food alternatives. Chemicals might be added to make food more nutritious or even to make it look better. In terms of yellow rice, some mac and cheese products. I'm not going to name names of brands, but some macaroni and cheese products, sometimes they're just chemicals are added just to make it look more yellow, like cheese. And that's up to you if you want to eat it or not. So for example, a serving of cereal fortified to provide 100% of the recommended daily intake contains 18 milligrams of iron. The recommended tolerable upper intake level is 45 before causing GI upset or making your kind of your colon or your intestinal tract very upset. How many bowls of cereal can you eat before you exceed that level? So what we would do is just divide 45 by 18 and we'd get about maybe 2 or 3. Here's a look at a goiter in the throat of this woman. And a goiter is usually symptomatic of an iodine deficiency. It affects the thyroid gland, which is located in your neck. And a goiter will sometimes just be an example of an overactive thyroid gland. So it'll form kind of a bulging area in the neck. Foods that are rich in iron, a lot of green leafy vegetables, beans, dried fruit, eggs, nuts, and red meat are very rich in iron. Mouthwash and toothpaste with added fluoride, that's common to add it to help with tooth decay. So then we get to the properties. Each element consists of one kind of atom. So the element sodium will have all sodium atoms in it. An atom is the smallest unit of matter that still retains the properties of an element. 3 subatomic particles are relevant to elements. And these 3 subatomic particles are neutrons, protons, and electrons. Neutrons and protons are in the atom's nucleus, or the center part of that atom, and the electrons will orbit around the nucleus or spin in an orbit outside of the nucleus. The unique number of protons is an element's atomic number. And this is important to recognize. The atomic number is assigned to each element in the periodic table, and the atomic number just refers to the number of protons that element has. An atom's mass number is the sum of its protons and neutrons in the nucleus. So if an element has an atomic number of 6 and a mass number of 12, you know that it has 6 protons and 6 neutrons because the mass number is equal to the number of protons and neutrons. So the atomic mass is approximately equal to its mass number, and isotopes of an element have the same number of protons but different number of neutrons. So for example, a nitrogen atom has 7 protons, which would be the atomic number, and its most common isotope has 7 neutrons. A radioactive isotope of nitrogen has 9 neutrons, which is a couple extra neutrons. And what is the atomic number and mass number of this radioactive nitrogen? So the radioactive nitrogen has 9 neutrons, just 2 extra than the normal one. The atomic number just refers to the number of protons. So that would still be 7. And the mass number would be the number of protons and the number of neutrons, which would be 16. So this is a look at how an element is made up with the same types of atoms. So this is an atom showing the protons, which will have a positive charge, and neutrons have a negative charge. Those are in black. And it's showing how the electrons are orbiting around the nucleus, and the electrons always have a negative charge. You'll see the electrons here in a single orbit, but the electrons normally follow more kind of like a level or a distance away from the nucleus, and they can kind of go anywhere within what we call the electron cloud. Here are isotopes of carbon, which again just means different numbers of neutrons. So the atomic number will always stay the same at 6 because that's the number of protons. And then the neutrons just change with different isotopes. Because the neutrons change, it changes the mass number because mass number is the number of protons and neutrons. So we label these different isotopes of carbon. carbon 12 based on its mass number, carbon 13 with 1 extra neutron, carbon 14 with 2 extra neutrons. And the number of electrons normally equals the number of protons. Radioactive isotopes are useful as tracers for monitoring the fate of atoms in living organisms. Very sophisticated imaging instruments can detect them. There are also some dangers associated with using any sort of radioactive substance. And why are radioactive isotopes useful as tracers in research on the chemistry of life? And that's just because in the chemistry of life, these radioactive isotopes can be seen with an imaging software system. So if you put this dye of radioactive isotopes in, you're able to kind of see this on an imaging, and it can be very helpful to detect things. So here's a technician monitoring the output of a PET scanner of the brain, which can be really helpful for detecting any sort of tumors or abnormal electrical activity of the brain. Here's the brain of a healthy person and an Alzheimer's person. It shows yellow, orange, and red on the front and back with a small dark area in the center and green and blue on the side. So an Alzheimer's patient brain looks very different from a healthy person's brain. And the use of radioactive isotopes, PET scans, can help detect that difference. So chemical bonds. Electrons can be located in different, what we call electron shells, or variations of distance from the nucleus, each with a different distance from the nucleus. And an atom whose outer electron shell is not full, meaning there's a spot for it to gain or lose an electron, will tend to interact with other atoms and either share, gain, or lose electrons, resulting in attractions called a chemical bond. The actual transfer of an electron between atoms results in an attraction called an ionic bond. So an ionic bond is just the transfer of an electron between atoms. A covalent bond are where atoms do not transfer electrons but will share them equally. And looking at the electron distribution diagrams for hydrogen, oxygen, nitrogen, and carbon, how many covalent bonds can each form? And it's hard to see this with a diagram, and I don't have one in here, so I'm just going to show you the one for carbon. So here's an electron distribution model of carbon. So because carbon has 1, 2, 3, 4 electrons in its outer shell, or the shell furthest away from the nucleus, that means it's able to share these 4 electrons and 4 covalent bonds. So carbon will often have 4 bonds associated with it, bonding to 4 other atoms. The periodic table, so this actually now shows the electron distribution diagrams of the first 18 elements. And the periodic table is made of 3 rows. The first row of atoms has 1 electron shell, so you can just see 1 shell, 1 blue circle around these 2 atoms. The second row of the periodic table has 2 electron shells, and the third row of atoms has 3 electron shells. And then each column has different amounts of electrons on the outer ring, 1 through 8 from left to right, except for helium, which is on the 8th row, but has a complete outer ring with 2 electrons. So that's a little bit how the periodic table is laid out. Here's more of the electron distribution diagrams. The periodic table again shows 3 rows. The first row, hydrogen has 1 electron shell. The second row of atoms has 2 electron shells, so 2 blue circles. And the third row of atoms has 3 electron shells, so 3 rings of blue. And then this is the other half of the table. Each column then has different amounts of electrons in the outer ring, 5 through 8 from left to right. So these will have 1, 2, 3, 4, 5 electrons in its outermost blue ring. This row, column 6, will have 6 free electrons in an outer shell, 7, and then 8. In a nonpolar covalent bond, electrons will be shared completely equally, and in a polar covalent bond, such as those found in water, electrons will be pulled closer to the more electronegative atom. And polarity refers to just a separation of charges. Think of a positive and negative pole of a battery. And because of this, the bonds in water molecule are polar covalent because they make little triangles, and we'll show you that here. So here's H2O. Because it's a polar molecule, the electrons will be more kind of attracted to the oxygen atom. So the oxygen atom will be more slightly negative, and it gives us this non-polar shape, meaning there's more positive on one side where the hydrogen atoms are, and more negative on this side where the electrons are kind of congregated. H2 hydrogen, the electron distribution is completely linear. O2, it's a linear molecule, and CH4 methane is a very non-polar structure because the electrons are shared equally. But water is a polar structure because the electrons are shared unequally. A little bit more here of hydrogen and oxygen. The table compares the electron distribution space to the space filling model for two simple molecules, hydrogen and oxygen. And two hydrogen atoms will share a single bond, which is a pair of shared electrons. Two oxygen atoms will share a double bond, which is just two pairs of shared electrons. And the double bond is shown, you can't really see it here, by a double line. And they both are linear structures, meaning they're nonpolar. And then here we have methane in water. A carbon atom in methane, the C, will share a single bond with 4 hydrogen atoms, and an oxygen molecule shares a single bond with 2 hydrogen atoms. The structural formula, this carbon is bonded to 4 hydrogens about equally around. So this is a nonpolar structure in CH4. And in water, H2O, the oxygen atom has a slightly negative charge, as the negatively charged electrons are pulled closer to it. And with its electron pulled closer to oxygen, the hydrogen atoms will have a slightly positive charge. And it gives us this little, not linear, but kind of an unequal sharing of electrons. And that's what we call a polar molecule. All right. And then this is again showing the polar molecule of water, H2O. Here's a great animation of covalent bonds. Again, please download the PowerPoint and watch these animations because they will greatly help. Then an ionic bond is an attraction between ions of opposite charge. An ion is any atom or molecule with an electrical charge resulting from the gain or loss of one or more electrons. Two ions with opposite charges will attract each other, and when the attraction holds the ions together, it's called an ionic bond. And salt is just a synonym for an ionic compound, which is sodium chloride, because they're oppositely charged compounds. Sodium is positive, chlorine is negative, and they will be oppositely charged together to create an ionic compound. So here's sodium, Na, and chlorine, chloride, and they will they'll share electrons, but they're both positively and negatively charged, so they'll attract each other to form an ionic compound. Sodium chloride. Sodium is positively charged and chlorine is negatively charged. And that's because sodium has one less electron in its valence shell, and chlorine has an extra one, which gives it a negative charge because electrons are negative. This is a crystal of sodium chloride, so it actually makes this crystallized structure when it is bound together to create the crystals that you can see as salt. And here's a crystal of salt. Another animation of ionic bond, great to watch. Please look at that. And then we'll kind of end with hydrogen bonds, and then we'll do part B of this later. Hydrogen bonds are weak bonds, but they're very important in the chemistry of life. They're one of the most important types of weak bonds. The hydrogen atoms of the water molecule are attached to oxygen by polar covalent bonds, And because of these polar bonds and the wide V shape of the molecule, water is a polar molecule. So water has an unequal distribution of charges, and what enables neighboring water molecules to hydrogen bond to one another. And that is because of the interesting shape of water, this H2O. The positively charged hydrogen atom will be attracted by a hydrogen bond to the negatively charged end of another H2O molecule. So the partial positives of hydrogen will be bound to oxygen of other water molecules through these hydrogen bonds. They're very weak, but hydrogen bonds are really important in your DNA, for example. They keep your DNA held together, but because they're weak, they also allow your DNA to be replicated easily and transcribed, which is important for making more proteins. So here's another great animation of the water structure. So maybe we'll stop here with part A and we'll finish with part B on chapter 2 in the next lecture recording. So thanks for listening, guys.